Okay, let's get started. So there is going to be another lab out this week, as I had indicated. Go to the discussion section tomorrow. Okay, there's going to be a discussion of the next lab. It's going to be on threads, all of the material that we have already covered. Okay. So before I begin, let me start with the occasional computing parable. This one is going to be on the donkey that starved, and it's apt for a rainy day. So the story goes as follows. There's a donkey that lives in a land that has famine, and there is not a whole lot of grass. The donkey is very careful whenever it finds even a single blade of grass. So it makes sure that it carefully feeds it and doesn't starve. And then after a while, the famine goes away, there's a lot of rain, and there's lush green grass everywhere. And the donkey is now very happy to see all this grass. It cannot make up its mind which part of the land would eat the grass from. It goes from one place to another saying this grass looks better, or that's even better, and doesn't eat anything and ends up starving and dying. Okay, so, so the moral of the story is, as you can imagine, grass is always greener on the other side. So don't rush after the next big thing and not focus on any one thing. I think focusing in a time of famine is actually better than not having any focus in time of riches, is the moral of the story. Okay. All right, so let's get going. So we are actually at the next logical point in the course in terms of topics. So we are done with processes, threads, synchronization, deadlocks. It's taken us a good dozen or so lectures to get there. So we have three more components of the code. They are somewhat shorter than the first one, which took us a significant amount of time. So the next one that we are going to start today is on memory management. So everything you've done so far is how do you deal with how does the OS deal with the CPU, anything that has to do with the CPU, whether it's process management, thread management, synchronization, and so on. So now we are going to look at what does the OS need to do to manage the RAM on the machine, the memory on the machine. So that's memory management. And then there will be two other pieces coming up in a few lectures. One is going to be I/O. What does the OS do to manage your I/O devices? And then the last one is networking. What does the OS do to deal with the network? Okay, the network part. Okay, that's distributed systems. So we'll start with memory management. Okay, so basically here are the kind of things we are going to deal with, at least to begin with. And I'm going to give you a quick recap of where the executing process is stored. Obviously it's stored in RAM, but we'll look at that in a little more detail. Okay, then we look at uniprogramming, okay, which is one process is resident in memory, and only one process is executing at any given time. That's a uniprogramming word. We look at memory management in a uniprogramming word, and we will look at what happens when multiple processes resident in RAM at any given time. Okay, what do you need to do? How does that work? Okay? And in the context of all that, we will encounter this notion of a memory address. How is it generated? How do you prevent a process from accessing memory that belongs to another process, and so on and so on. Okay, so we'll start with several simple techniques today. We'll continue the discussion. We'll talk about more advanced techniques like paging and on-demand virtual memory. Maybe next class or at the end of this class we can start talking about this. So this is the picture I put up in lecture 2. Okay, so these are the 4 key components of the machine, and you will see that we have blown up a few more here. Okay, the processor, which was one box, now we have some components in this actual processor itself, but we have put in some caches and so on. Okay, there are another 2 types of caches. One is an instruction cache, another one is a cache called a TLB, translation look aside buffer, that we are going to encounter in a lot more detail in the next few classes. Okay? And that caches are obviously pieces of memory, faster memory than RAM, where you keep more frequently accessed data and or instructions, okay, so that the execution of the program can be sped up, okay, rather than fetching data or instructions from a slower, somewhat slower RAM. Okay. if you store that in a faster memory, such as a L1, L2, L3 cache or in the TLB, then we can actually improve the performance of the process. Okay? So that's the picture to keep in mind. We still have memory here, and the memory controller will talk about that as well. Okay? So the way we discussed this in lecture 2 was we said there's a difference between a process and a program. Program is simply a set of instructions. It could be source code that you write. Okay, let's say it's in C, then if you have to run this through a compiler, it generates machine code and execute a binary. Okay? That's also a file that's stored on disk. Okay? Or you may have Java, in which case you stick with source code and you let the Java virtual machine actually execute. But in either case, when you start executing this program, whether it's a Java program or a C or a C++ program, you have to first bring it from disk into memory. Okay, that's the part of setting up the process. Okay, so the OS is going to load the program into memory. Once the program is in memory, then you actually start executing the program, which essentially means you take the first instruction, you execute it, you take the second instruction, execute it, and so on. So you sequentially execute instructions, you may have loops and so on that cause you to jump to other parts of the program, or you may make function calls, but nevertheless, you basically have to fetch instructions from the process that's loaded in memory, and then the CPU is going to execute. And as part of executing the instructions, you may access variables that can be also stored in memory that require you to go back to memory and look up the value of that variable and so on. Okay? So that's the picture to keep in mind. You have a program, you load it into memory, it becomes a process, you start executing the process, which essentially means you fetch instruction and or data one instruction at a time from memory, okay, and then you execute. Okay? So the execution of a process is going to require you to access the memory that's allocated to that process. Any questions on this? Okay, this is just a quick recap, but nevertheless, it's an important thing to keep in mind. Okay, so now let's start with some terminology before we talk about memory management schemes. Okay, so we'll talk about three terms here. First one is called a segment. Okay, a segment is simply a chunk of memory, contiguous chunk of memory that is allocated to a process. Okay, so if you have a chunk of RAM allocated to a process, that's referred to as a segment. Okay. A physical address is a real address that is allocated, not allocated, the real address in memory. Okay. So if you have some number of bytes, let's just call them words, 0 through n, okay, those are physical addresses. Okay, so in this case, you'll see that this memory, okay, has addresses going from 0 to 2400. That should be 2399 because you always start from 0. So if you have 2400 words, it goes from 0 to 2399. Okay? Those are called physical addresses. The actual address of a RAM location. Okay? Now, virtual address, on the other hand, is an address related to the start of the process. It's not a physical address. So in this case, you have three processes, A, B, and C, that are resident in RAM. There's also the OS kernel that's resident in RAM. And you will see that, let's just take the B example of B. It's loaded from address 200 to 2399 in physical. Those are the physical addresses. Okay, that's the part of memory where the process is loaded. But that process is 400 words in length. So it has virtual addresses going from 0 to 399. Okay? Those are addresses related to the start of the process. Okay, so keep this in mind. So there's a distinction between the notion of a physical address, which is an actual location in RAM, and a virtual address, which is the address related to the start of that process's address space. And we'll come back to why this is important in just a moment. Okay, so these are three terms to keep in mind. Okay, now let's ask the question, where are the addresses actually being generated? When we have a process that's executing, where do addresses come from? Okay, so we'll look at three different options. You can generate these addresses at compile time, load time, or execution time. Okay, so what does this mean? Okay, let's take the compile time example. So let's say you've written some source code, and maybe you just take a very simple instruction of doing an assignment. Let's say you say this in your code. Okay, you just say I is a variable, you assign the value 1. Okay? What is happening as far as your machine code is concerned? Your compiler has to allocate a region of memory, okay, within that program to hold the value of I. Okay, you allocate some, let's say, a word or an integer to store I, And when you have to execute this statement, you are going to essentially load I into a register, okay? And then you are going to assign the value 1 to a register, and then you basically store the register back to I. This is how this one way to execute that statement using a set of assembly instructions. Okay? You may have assembly instructions that directly allow you to store a value to a memory address, but in simple architectures, you have to take that memory region, put it into a register, do that assignment, which is assign that value into, write that value into register, and store it back. Okay? So this would be a piece of assembly code that is going to execute that high-level instruction. Okay? Now the question is, you have to assign actual addresses within machine code. I is meaningless. You have to actually have a memory address there. That's the address that you are actually going to write in it. So it's the actual process. Okay? And let's say this is where the compiler decides to store I. Let's say that's address 200. Okay, so it just allocates some region, and maybe that's the region in stack. Okay, so then this is going to be address 200, and this is going to be address 200. So this is what the compiler would have to do. It would have to allocate a region wherever it has to manipulate I. It's going to actually write out the address of I. Okay. So this is referred to as generating these addresses at compile time. The compiler is laying out the variables in RAM. It's assigning addresses to those variables, and wherever the variables are being manipulated in instructions, it is going to use those addresses.
What did you write next to 11?
I just read, okay. It just says address. I'm just using some pseudo assembly instructions. So you basically, rather than saying load I into a register, you're going to say load whatever is stored in address 200 into a register, because that is where you're going to store I. This is how you're going to translate a high-level source code instruction into some assembly instruction and assign addresses to them. Okay, so this is again going to be address. Okay, so this is compile time. Okay. You could also do this at load time. If now what this is assuming, of course, is that you know where in memory your process is going to actually be loaded. So that is why you can write physical addresses into assembly instructions. But typically when the compiler is compiling the code, it may not know when the process actually runs, where it's going to be resident in RAM. In this case, you have two other options, which is you have, let's say, just I here, and then at load time, when the loader is actually loading your program into memory, you are going to look for the actual address and substitute it. Okay, or you will see techniques where you have logical addresses and you actually translate them into physical addresses by actually scanning instructions and putting in actual address values. Because at load time, you know where the process is going to be loaded. So if you say I is the 20th byte from the start of the process, you know the physical address of that location. You can put it in here and then load the process and start executing it. Okay? Or you can do this at runtime. Okay? If you have things like dynamic memory allocation, okay, where you allocate an object, you run new or some such thing, or you run a constructor, at compile time you don't even know where the address of that object is going to be. It's allocated at runtime. So you have to actually assign addresses at runtime. Okay, so you will have these three options: compile time, address generation, load time, and execution time. Okay, some of these techniques are suitable in certain scenarios, but not in others. Okay, is this clear? Any questions here? Yes.
Yeah, so these all mutually exclusive, like one thing happens.
The question is, are they mutually exclusive? By and large, yes, but not quite. Okay, so for instance, you may do some load time address generation, but if your process is doing dynamic memory allocation, you call malloc, you call new, you don't know at load time what that address is, so you have to combine this technique with execution time, for instance. Right? So, yes.
For the load time, you say the compiler generates an address, is that the actual address?
Yes, so as we will see at this point, I didn't actually provide the details, but if you are going to do either the first one, okay, compile time, if you knew where the process was going to be loaded, you can generate physical addresses. Otherwise, the compiler has to generate some address. It's going to generate a virtual address. that you either translate as load time or execution time, as you will see. These are just terms or just concepts at this point. When we talk about specific memory management techniques, you will see how these techniques are actually applied for a specific scheme. Okay, so this is basically how addresses are generated, and we are going to start very simple. We are going to look at very simple memory management schemes and start building on them. Okay, so first scheme we are going to look at is Uniprogramming. Okay? So in this case, you basically have only two things loaded in memory: the OS kernel and the process that's executing. Okay? So if you have some RAM, there's a process, because only Uniprogramming, only one process loaded in memory. So the process is loaded and the OS kernel is also resident. Okay? So what we can assume is that OS is always loaded in the high memory region, meaning that it is loaded in the last part of your RAM. And we'll assume that processes are always loaded starting at address 0, okay, since you have only one process at any time. So the picture to keep in mind is you have RAM in Uniprogramming, so this goes from 0 to n-1 for n words. Okay? So your OS is here, okay? And if you want to load any process, you are going to start it at address 0. Okay? So here is process A. Okay? So it goes from 0 to k minus, so it has k words in it. Okay? So in this case, since you are in Uniprogramming world, the compiler actually knows where the process is going to reside. All processes always start at address 0. There's only one process at any given time, so you can load it at address 0. Okay? So what that also means is compile time address generation is going to work. You can directly compile and create physical addresses for each of these variables that you have in your program. So you know precisely where that variable is going to be stored in physical memory. Okay? So compile time address generation is going to work if in a Uniprogramming world. Okay? So the process always starts at address 0. You always assume that you give it a contiguous chunk of memory. Okay? So this is contiguous, as you will see. Okay? Compiler can generate physical addresses. And last but not least, the maximum size of a process that you can support in a Uniprogramming environment is the size of RAM, amount of memory you have in your machine, minus the size of the kernel. Okay, so the kernel takes up some space. Whatever is left over is whatever you can allocate to process. That's the maximum size of a process that's allowed. If the process size is bigger than that, you can't execute. Okay, in this case. Okay? And we look at the last point, which is the OS needs some protection in this case. So you still need to do some checks, and the process is accessing some region of memory. You have to ensure that it only accesses regions that's basically within this space, 0 through k minus 1. You're not allowed to access the OS's memory and trample on it or something like that, which will cause problems. Okay. So that's Uniprogramming. Okay, here's a picture of Uniprogramming, same picture I drew here. Okay, so you have three different scenarios. In one case, process A is executing, it's loaded in high memory region. Okay, once A is done, you can then load B and execute B, and then you can load C and execute C. Okay. Now, as you can imagine, this does not allow you to do any overlap of I/O and computation. If you have a single process loaded, process starts doing I/O, it cannot execute anymore. CPU will become idle while the process is finishing its idle. Okay? So you are wasting your CPU because there's nothing else to run. There's only one process loaded in the day. Okay, that was the reason we said multi-programming is a better approach. It allows you to overlap I/O and computation. Some processes are doing I/O, others may still be on the ready queue, you can execute them. Okay, so we are going to start looking at Uniprogramming next. Any questions on multi-programming next? Is there any question on Uniprogramming? Okay, so now let's talk about a multi-programming environment. Okay, everything we talk about from now on will assume that multiple processes are resident in memory. Okay. So we want three properties from our memory management technique. We want something called transparency. Okay. What that means is process A should never be aware that there are other processes running. Okay? It should look to process A that it owns its memory and it can do whatever it wants with the memory allocated to it. The presence of other processes is hidden from it. From a memory management perspective, it shouldn't matter. Okay? So this is called transparency. So we want multiple processes to coexist in memory. No process should be aware that memory is shared. Okay? And processes should not care what portion of memory they have loaded in. Okay? Since you're multi-programming, in a multi-programming environment, not every process can start at 0. Only one process can be the one that's loaded at address 0. Others will obviously be loaded in other regions of memory. Okay, this should be transparent to the process. Where it's loaded shouldn't matter. From an execution standpoint, it should execute the same issue. Okay, we'll see how to do that. These are just properties that we want. Okay? The other property we want is safety. Okay? Processes must not be able to corrupt one another. Processes must not be able to corrupt the OS. So what that means is each process should only be able to access the region of memory that's allocated to it and nothing else. It shouldn't be able to allocate access addresses that do not belong to the region that or the segment that's allocated to it. Okay, that's the safety property. And the last one is efficiency, which we will see also the performance of your system. Okay? As a result of any memory management technique you adopt shouldn't get degraded because of that thing. Okay, we'll see the only way to achieve that is to actually have extra hardware support. Okay, without hardware support, any multi-programming scheme will result in slowdown, as we will see. Okay, because of the address translation that must go on. Okay, so now we'll see some techniques to do this. The first one is called relocation. And we'll see two variants of relocation called static relocation and dynamic relocation. But the basic idea is very simple. Okay? Again, we are going to put the OS in high region of memory. But now we will let multiple processes be resident in RAM. Okay? And now what we will do is when the compiler compiles your code, it doesn't know where the process is going to be loaded. In fact, if you start the process multiple times, it may get assigned to different regions of memory. It can't even be loaded in the same place if you start it up different times or multiple times. Okay. So what we will do is we will simply allocate a contiguous segment of memory. Okay. And we are going to somehow make the process not realize that it's in different regions of RAM. We'll just make that completely transparent to the process. We'll see how to do that in just a moment. But here is a picture we have. So you have A and B loaded in memory. Process C starts up. It needs 300 words. Okay, so you just find an empty region that's 300 words long. That's the gray region that's shown there. That's all unused memory. You just take 300 words from it, you assign it to C, and then C is basically going to be resident in the region allocated. If D comes along and it needs some region of memory, you'll again look for a contiguous chunk in the gray region, and an unallocated region, and allocate that space to D. Okay? So this is how memory management is going to work. When a process comes, you look at the size of the process, you look for a region of memory that's unused, that's at least that big, and you allocate that region. And that's where the process is going to reside over its lifetime. Is that clear? Now, what does this relocate? What does this have to do with relocation? We'll define two terms and we'll see how this is going to work. So, whenever a process is loaded into memory, the starting address of the process we'll refer to as the base address. Okay? The ending address of the process is going to be the limit address. Okay? So, we should ask, what's the base address for A? It's 400, and the limit address is 899. Yes, or 900, doesn't matter. I didn't say what the size is, but let's say it's 500 more. So it's going to start at 400 and at 899. Base address is 400, ending address is 899, and I'll see how to use that. Now, if you use the static relocation variant of the scheme, what now you have to do is when you load the process into memory, since A starts at 400 and ends at 899, you have to go and adjust all the assembly instructions that access any region of memory and put in those physical addresses. So when the compiler compiled the code, it assumes that you started at address 0. But when you actually run the code, you're starting at address 400. So all the addresses that the compiler has generated have to be adjusted by a value of 400. Okay? In other words, you have to add 400 to every memory address in any assembly instruction. Okay, is that clear? What I just said? Because the compiler doesn't know where you are going to be loaded. So let's just take this example here. Okay, so when the compiler compiles, it assumes This is A, it starts at 0, it ends at 499. So let's say it puts I at region 20. Okay, this is what the compiler assumes will happen. Okay? When you actually load A, as you will see, it started at region 400. Okay, location 400. So this is what has actually happened. Okay. So any memory instruction that accesses I will have an address of 20 in there. Okay. But what's the actual address of I in this case? It's going to be 420. Okay. So essentially what you have to do is take the starting address, okay, and add it to every memory address. You have to add that offset to every memory address, and that will give you the physical address. Okay. And this is done by what is called the loader. Okay. Loader is simply a piece of program that is tasked to load your program into memory. Yeah, so in addition to simply reading the data and sticking it into memory, it has to do extra work. It has to scan your code. Every time you see a variable with an address, you have to add 400 to that address because that's the real address of that variable. The compiler generated it, it thought that the process would start at 0 and it generated addresses accordingly. But the process actually starts at a different address.
You load the program or process?
Sorry?
You load the program or the process?
You load the program and it becomes a process. Terminology is program is a piece of code that resides on disk. When that piece of code is executing in memory, we call it a process. Okay, so when you load the program, it becomes a process. The process is simply an executing instance of a program. Okay, but is that clear what static relocation is? So at load time, you are going to adjust the addresses within the process so that they actually refer to the real addresses. If you did not, then you would have errors. Because this process may start accessing address 20, it doesn't even belong to it, that may belong to some other process. So all your program would run. So you have to do this adjustment at load time. This is called load time address generation. That's what I was mentioning earlier. Okay, that's one approach. Another approach is not to do anything at load time, but instead do things at runtime. And this is referred to as dynamic relocation. Okay? And the way this is going to work is you are going to use some extra hardware to do this adjustment at runtime. Okay? In particular, you are going to add 2 extra registers. Okay? One is called the base register, or also referred to as the relocation register, and the other one is called the limit register. In the base or the relocation register, we are going to put the starting address of the process. In the relocation or the limit register, you are going to add the ending address of the process. So for process A, you are going to store value 400 here and value 899 here. Okay? And what do these 2 registers do? Okay, so every time your CPU is executing an instruction, you look at, is there a variable in that instruction? Okay? You take the address of that variable, okay, which is going to be a logical address, okay? And then you basically do this logic. Okay? You take the value in this register, you take the logical address, you sum the 2, that gives you a physical address. Okay? So in particular here, since the compiler has, in this case, the compiler has generated code assuming the process starts at 0, your variable I is going to have address 20. Okay? That's your logical address. Okay? So you load an instruction that still has address 20 in it. When you try to execute that instruction, you are dynamically going to translate that address 20 into real address. Okay? So you will take 20, you have 400 here, this is going to happen transparently. Okay? For every address, you are going to take the base address and add it to that address. Okay? That's the CPU is going to do that for you automatically. So you take these 2, you'll add it, that's going to give you 420. That's the real address in memory for that variable. Okay. So this is going to happen for every single address. So you're doing the translation at runtime. Address, this is referred to as address translation. Okay. You take a logical address, okay, translate it into physical address. As I said, logical addresses are addresses that the compiler has generated, assuming the process starts at location 0. Okay. Physical addresses are real addresses. Okay. So what is the limit register doing? So what you are also going to do is you have a comparator. Okay. You are going to see if the address that you have exceeds the size of your process, and if so, you throw an error saying that you are trying to access an address that's out of bounds. Okay. That's your check to prevent this process from accessing any region of memory that doesn't belong. that clear? Okay, so this is simple comparator. It's only checking whether you access addresses that go beyond the process input. You actually have to check on both ends really. You cannot access anything that is before the start of the process or after the end of the process. That one is only checking whether you access something beyond the end of the process. Okay, but that's for simplicity, that's good enough for you. Okay, so you have extra hardware in your system to do this. And this is where efficiency comes in. Okay, now if you have to actually have to write assembly instructions to do this, every assembly instruction will turn into 3 or 4 assembly instructions. Okay, which is you're going to add all this and generate at runtime. That's going to slow down the process execution significantly. So we use hardware to do this for us. With this hardware, you need an adder and a comparator. Okay? That's fairly cheap to put in. If you know anything about digital logic, if you have an adder that's just going to take 2 values and do a Boolean add of it. The comparator, you do Boolean compare. Those are efficient operations. So we'll say that this can be done efficiently without really impacting the performance of your executing process. Okay, every assembly instruction that has a memory address, you are going to do one add and one compare. But that's being done in hardware, not in software. Yes.
So where is the limit register being stored? Is that also treated by the memory?
Yes, so there are 2 extra registers that your hardware needs 2 extra registers and an adder and a comparator. There's a base register, there's a limit register, there's an adder, there's a comparator. This is all the extra hardware you need at the CPU in order to implement dynamic relocation. Without that, you cannot implement it efficiently. Okay, yes.
So those are like physical things on the CPU.
Yes, yes, you need hardware support in the CPU to do this.
Those common for today's systems to have those.
Yes. Question is it common? Yes and no. Yes, in the sense that that is the only memory management scheme your CPU supports. You will at least have those 2 registers and all those values. The reason I said no is this is a very simple technique that most CPUs do something far better than that. So they actually don't have the real hardware, they have something else that's also extra hardware, which is encounter, which is going to provide page table support and so on. Okay? So the point you need to keep in mind is you need support from the CPU or the hardware in order to implement this. Otherwise, the scheme is going to be really slow because you have to do all this extra work in software, which is every assembly instruction you have to do all these extra checks and so on and translation. That's going to slow you down. And you don't want that performance hit, so you want hardware support. Okay, yes?
So 400 is just a number. So if we ask like what's the physical address of 8, then 899.
What is the physical address of 8?
No,
8?
like what is 400? It's not like.
Okay, so what is 400 words? So we are assuming A is a process. It's 500 words. And in this case, we assume that it's loaded starting address 400. This is the starting address of the process. It's contiguous and it ends at 899. That was the reason I have that example is just taken from what is there here. Okay, you see that in this case, there are 3 processes and you see that A started at address 400, ends at address 899. C starts at 900 and ends at 1100. Okay, so, do you have a question?
I was wondering if it's just like a number or
Oh, what is 400? That's just so. Okay, so now I understand the question. So memory has addresses. That's how you actually access a region of memory. You specify an address and you go to that address. So you basically have bytes. Think of memory as addressable bytes. Okay, so if you say address 1, that's the second, or address 0, that's the first byte of your RAM. Address 1 is the second byte of your RAM. Address 3 is the 4th byte of your RAM. So address 400 would be the 401st byte of RAM. That's how you access RAM. Okay. Any other questions here? Yes?
Would it be okay to think memory is just a giant array of bits?
Yes, so you can assume it's a giant, not array of bits, it's an array of words. You can't address bits, you address words. A word could be 1 byte, it could be, depending on whether it's 8-bit memory or 64-bit memory, address a 64-bit word. Okay, so the way things are going to work is you can address words in memory. Think of RAM as an array of words. Okay. Address 400 will allow you to access 400 words. That's how you The CPU says 400, you go and fetch the 400th word in your lab. Okay, is that clear? Any other questions here? If you don't understand memory addressing, you should ask, because then memory management won't make any sense. Yes?
If it's in words, then if you just like allocate like true or false, like a 1-bit piece of information that uses up a whole word.
Yes. If it's a word is the minimum granularity of what you can allocate. So if you have 1-bit variable, it's going to take a whole word, unless your compiler is smart and is stuffing multiple variables and it's going to address a particular bit, but that requires more work. So the same thing is true if you declare a byte in your program as opposed to an int. A byte is 8 bits. An int may be 64-bit if you have a 64-bit machine. Your words are 64-bit. A byte will still fit within a word and you may waste the remaining bits of that word. So that's how compilers do things.
If you have multiple processes running at once, does the hardware have multiple base models?
Okay, that's a good question, right? So here we have 3 processes. Okay, the question is, if you have multiple processes, does the hardware support multiple relocation and limit register? Okay. So the way things work is the hardware supports 1 base and 1 limit register. And when you do your context switch, you are going to actually decide which process runs next, and you are going to take its value of base and limit and put it in the registers. Because only one process is executing at any given time, you only need 1 base and 1 limit register. When you switch to another process, you are going to take those values and put it back in the process control block and load the new values. Okay? So this is what we meant by you save and restore memory management information as part of your context switch. The memory management information you are storing and restoring are, in this case, only base and limit registers. Okay, they are unique to each process, but there is only 1 register, okay, 1 base and 1 limit. So you will have to use that for each process. Okay, okay, so this is, yes, sir.
How if it's a multi-core computer?
What if it's a multi-core computer? Then you will need 1 per core, because you will have 1 process executing per core. So since here we assume single core, that means you will need 1 for that. But yeah, if you have multiple cores, you will need multiple base and limit. Okay, so that's dynamic relocation. So quick advantages and disadvantages. The advantage of dynamic relocation is that OS can easily move a process during execution time. So you should ask, why should the OS even bother moving the process? Okay, so it should be clear that you can move the process. If you just decided you want to put A somewhere else, you can move it somewhere else, and all that changes is the value of the base and limit register changes. If you did this for static relocation, if you move a process, you have to go and rescan the code and adjust all the addresses again. So just there's like you add 400 to each of the address, you have to do that all over again. But in your dynamic relocation, you can move the process wherever you want, and then all that changes is the base and limit. Nothing else has to change in the code. Okay? So that's great, but why do you even want to do a process? What does this achieve?
If you allocate a bunch of things to the heap, you might run out of space and it's implemented into the processes.
Okay. So the thing that we haven't said yet is that process sizes are not going to stay fixed over the execution of the process. Processes will grow and shrink. As you allocate memory, if you start allocating lots of objects, you will have to allocate more RAM. If you start doing mallocs or new in C++ or you run a constructor in Java, or you deallocate, the process size will shrink. Okay? So processes won't stay fixed in terms of their memory sizes or the execution of the process. So now what does that mean? If you actually laid out the process the way we have shown here, you'll see that there is no room for A and B to grow if they stay there, because there is another process right before and right after. Okay? Now if you run a constructor in there and try to allocate more memory, 1 or 2 things have to happen. Either return an error saying I don't have any room to grow, or you have to move the process somewhere else and allocate a bigger chunk to that process. This is the only way you are going to make the process grow. Okay? C can grow in this case because C has one side of C actually has unallocated space, so C can grow, but A and B cannot. The only way they can grow is you have to actually move the process. Okay? Yes.
So when you look at the add, like the move distance
Yes. So if you move it, if you're done static relocation, you have to add the move distance to every instruction. For dynamic relocation, you just change the start and the ending address. You only change the register values. The code itself doesn't change at all because you still have logical addresses. Those haven't changed. All you did is you moved it to some new location. You put that location value here, and that's going to do the addition at runtime anyway. You don't have to do anything else. Okay. Yes.
Dynamic relocation, you can move the process once execution starts.
Yes. You can move the process after execution starts. Yes. If the process grows, no need to move it once.
For dynamic relocation, if you move the base and limit registers to outside of where the old area was, would you still have to move any variables that were stored in the old area to the new area?
Okay, so yes, so question is what does move mean? Move means physically copying whatever that chunk of memory is into some other chunk of memory. So everything is just being copied over. So your copy of you are not moving variables, you're moving the entire process. Okay, so what would happen in this case? You take that entire region, allocate it to A, you copy everything, all the code, all the data, everything moves as is. Okay, but now you have more memory to allocate to a process. Yes.
I think kind of what she was asking is that for a stack within a process,
Yes.
are all variables on that stack less the offset located in the relocation register?
I'm not following. Can you repeat the question? So you have a stack, and there are objects on the stack.
The stack. So are all the variables stored on that stack decremented by the value of the relocation register?
So let me draw a picture here. So this is our process A. Okay? And if you remember, we said processes, the way things work is you have code, your stack, your heap at the very least. There are 3 parts to a process. We just assume it's one big block, but there's still going to be some code here. Okay? And then let's say that's your stack. That's going downwards, and then the heap. And we go this way. Okay? So now there is a variable on the stack here. Okay, that's I. That's what we guess you can't see that. But there's I here. Okay. I has a value. Okay, this is the same example we had. Let's say that's address 20. Okay. And then depending on where process A is loaded in memory, you are basically going to have I stored at 420. That translation is happening at runtime. Okay. Now if you move this entire process, okay, you just copied the whole thing, so the picture remains the same. It's moved from here to here. Only the base address changes. It's still at the same location relative to the start of the process. That has not changed at all. Okay, it's still at word 20 relative to the start. So if you just use the base register or the relocation register, it should allow the translation to happen. Okay. Yes.
Well, more what I was asking is you said static. For static, if you want to move the process, you have to move the whole thing.
Yes.
But for dynamic, you don't have to. All you have to move are the 2 registers. But if you're moving.
Oh no. You have to move the whole thing and adjust the registers.
Oh, okay.
In both cases, you are moving the process. In one case, you are moving the process and actually changing the physical address in the code. In another case, you simply move the process. You don't touch the code. You simply change the values of the base and the relocation registers. So the process is moving in both of those cases. There's no other way for you to grow the process. Because the processes in this is called contiguous allocation. Process has to be one big chunk. You can't chop the process into smaller pieces yet. Okay, that's the next scheme you're going to study. Okay, so the process has to move. If you want to expand A, you have to move all of A, not only parts of A. Okay, so that's dynamic relocation and static relocation. So we said process can move, you allow the process to grow. Hardware is straightforward. You need 2 registers, adder and a comparator. Okay, disadvantage is, yes, hardware is fast, but disadvantage you still need extra hardware. It's going to have small performance degradation, not a whole lot. You tolerate it. You cannot share memory between processes yet. Okay, memory that you allocate to process cannot be accessed by any other entity. Process still has to be no greater than the size of RAM. We cannot yet support processes that exceed the size of RAM. So 2 GB RAM, maximum process size cannot be more than 2 GB. It's actually 2 GB minus the size of the OS. Okay. You'll see how to relax that and make processes bigger than RAM. Degree of multi-programming is limited because all processes have to reside in RAM at all times. So if you have 2 GB of memory, each process takes half a gig. You have no more than 4 processes that can run. You start a 5th process, you are going to say no, I don't have memory to do that. Okay, so the amount of degree of multi-programming depends on the size of RAM, which basically means all processes have to be present in RAM at all times. All of these we can relax. We'll see techniques that will relax each of them. And this will do, obviously it's a little more complicated than uniprogramming, as we've seen. Okay, so these are advantages and disadvantages. But the good news is we achieved all of the goals we started with. Is it transparent to a process? Yes. If process A doesn't know about the presence of process B and C, it is spitting out addresses assuming it's starting at location 0. The hardware is doing the translation at runtime. It doesn't know that it has other processes running. It thinks it's running at location 0, although it's loaded in some other region of memory. Okay? It is also safe because every reference is being checked with using the limit registers. You do not allow the process to access anything but what has been allocated to it. Okay, so you cannot go and start corrupting some other process's memory. Okay? And it is efficient because we try to use some hardware features to speed up memory translation. Okay? And we say hardware is faster than doing this in software. Okay? Now the only problem with efficiency is we do not allow process growth efficiently. If a process grows, you may have to copy that entire process, everything that belongs to it, to some other region of memory that has more space, okay, and that's going to be slow. That's not fast. Okay, so if you have a half a gig process, you have to copy half a gig of RAM from one location to another. Okay, so before we try to relax these things, we are going to study some other advantages or disadvantages of this technique. And to understand that, we are going to look at what happens in the continuous memory allocation over long periods of time. Okay, so here is a picture that shows how memory is used over different points in time. So if you assume that you start initially your OS loaded and 3 processes A, B, and C running. Okay? At some point in time here, B has finished, is departed. Okay? So when B terminates, you deallocate the memory that's being allocated. Given to it, so you see that gray means it's free, that the region of RAM is not included. So this region got deallocated, so now you have some extra space that's gotten created in the RAM. Okay? And then if they say D comes along, D needs some region of memory, we're going to allocate some part from here, so D goes there, and at some later point in time, A finishes, A goes out to deallocate its region, and then we basically get a free space there. Okay? So processes are going to come and go. Okay? As new processes come, you allocate memory to. As processes finish, you deallocate regions that are allocated. So what this is going to do is over some period of time, you will see that there are some processes resident in some regions, and then there are some other regions that are unused. Okay? Any unused region you are going to call a hole. Okay? Hole is simply a piece of free memory. Okay? Any gray region in this picture is a hole. That's an unallocated region of RAM. Okay? So at any point in time, you are going to have some number of holes in RAM and some processes that are resident in RAM. Okay? So when a new process comes in and says, give me n words of memory, you are going to actually have to look for a hole that's big enough and allocate that region. Okay? And we'll see there are 3 different policies to allocate memory to a newly arrived process. Okay? So we'll look at 3 techniques. One is called first fit, there's another one called best fit, and the third is called worst fit. Okay? What all of these policies are doing is, given a list of holes that you have in memory and a newly arriving process, you're simply asking the question, where in memory should this process go? Which hole should I use to, for this process? Okay? So what first fit does is assume that you have this list of holes, it's going to start scanning. And the first hole that is big enough is going to get allocated to a process. What best fit is going to do is it's going to scan all the holes and not just take the first one. It's going to find the best fit, which is a hole that's just big enough, okay, to accommodate the process. And the worst fit does the opposite. It allocates the largest one. So the best fit is the smallest one. It's big enough. This is the largest one. And the first fit is simply going to pick the first one. Yes.
How does the OS deal with severe data fragmentation?
Yes, we are going to talk about fragmentation for the next 2 slides. Okay, just hold on. So what this says is, now let's take this scenario. Okay. So you have one hole that's 500 words, this is 300 and this is 300. So if a process comes along and says, I need 250 words, okay, that's the amount of RAM I need, first fit is going to scan it and put it here. Because that's the first hole that's big enough. In fact, all 3 of them are big enough, so you just look for the first one. So process E is going to go there. To do best fit, you're going to scan this and say which is the smallest hole that's good enough. In this case, both of these are the same size, so you're going to randomly pick one, and actually the process will go there if you pick that one. Okay. The worst fit is going to look for the biggest one. Okay. In this case, the biggest one is the first one, and put it there. Okay. Yes.
Why would you use worst fit?
We'll talk about why does it actually matter. Worst fit seems really bad, given the name. Okay. So before we even talk about any of that, let's talk about fragmentation. That was the question that was just asked. So now, what does fragmentation mean? Okay. So if you look at processes coming and going, you will see that over long periods of time, you will have lots of holes scattered in RAM. Okay. Those are all processes that departed at some point in time and freed up that piece that was allocated to them. Okay. Now, so you will see your memory is getting fragmented because your processes scattered everywhere, holes scattered. And then eventually you are going to get this phenomenon called fragmentation, and there are 2 kinds. One is called external fragmentation and one is called internal fragmentation. And external fragmentation is said to exist when there isn't enough memory to, there isn't a hole that's big enough to allocate to a process, but if you add up all the free memories, there's still enough space to allocate to a process. Okay. So this phenomenon is called external fragmentation, and just to go back to the previous example, here, so you will see, if I ask what is the amount of RAM that is free in this case, how many words of RAM are available? Let's say bytes. Okay, so there's 500 here, there's 300 here, there's 300 here. Okay. So that's the amount of free space you have. Now if, let's say, a process comes along and says, I need 600 bytes of RAM, what would happen? So you look for a hole, saying, is there a hole that's 600 bytes in size? There isn't. There's one is 300, there are 2 holes of size 300, there's 1 hole of size 500. Okay. And if you ask the question, is there, what is the amount of free space I have? That's 1100. Process comes along, it's asking only 600, and you say, sorry, I do not have enough RAM. Doesn't sound right because you have 1100 bytes free, but there isn't 1100 bytes of contiguous space. That's the problem. Okay. So we have fragmented memory. Okay. All our free space is scattered. It's not in one sort of contiguous chunk. And as a result, process comes along, it's not asking for a lot, yet you cannot satisfy its request. And you tell the process, not enough RAM, cannot start this process. The process cannot run. Okay. This is called external fragmentation. Okay. So whenever you have contiguous allocation, you are going to have this problem of external fragmentation, which is that if you sum up all of the holes, you have enough free space to satisfy requests, but no single hole may be big enough. There isn't a contiguous chunk that is big enough to satisfy a process. Okay. So the reason this happens is frequent loading and unloading of programs or processes causes free space to be broken up into lots of little pieces, lots of little holes, and eventually the holes become small enough and there are lots of them scattered everywhere that they are not very useful, okay, to satisfy any one process. Okay. Now, there is this rule called the 50% rule, which basically says that if you have, on an average or long period of time, if you have 2 n chunks allocated, meaning that there are 2 n processes, then roughly n chunks are lost to fragmentation. Okay. Or put another way, whenever you have continuous memory allocation, approximately a third of your memory is wasted in little holes that are of no use. Okay, they are not big enough to accommodate anything useful. Okay, there are lots of little holes spread over. So roughly 33% of your, this is not a law, it's just an empirical observation. It says when you do continuous allocation, assume that a third of memory is going to go to waste. Because there will be, for long periods of time, you are going to have little holes that are just scattered everywhere, can't make good use of it anymore. Yes?
Does the 50% rule assume that all processes have the same size, or some particular size?
50% rule doesn't make any specific assumptions about processes. It just says if you have different size processes, they come and go, and then you basically look at how your memory allocation evolves over time. As we have seen here, that's an evolution that started with one hole at the end, and then here you ended up with 3 holes, and then if you keep doing, you'll get more holes and so on. There are processes of different size. Roughly speaking, you'll waste a third of memory on an average.
And what is a block considered, I guess, lost to fragmentation?
When is it considered loss of fragmentation? It's never really lost, because you can always get a process that is small enough to fit there, but after a while it may become so small that no realistic process may be able to fit in that piece. Okay? And when is it small enough? That depends on typical size of processing. I mean, let's say 10 kilobyte block may not be useful because there's no process that's going to be that small. Okay? But you can have a 1 megabyte block that may still be useful in some way. Yes, question?
Is classified versus the only free no allocation?
Okay.
I guess that would be used, or is there like
Okay, question is best fit, first fit, and worst fit only 3 policies? No, you can come out with any other policies. These are just 3 simple ones to think about when we think about continuous allocation. Say, I have a list, so the way you do memory allocation, you have a data structure of holes. Okay, think of it as a list, it could be some other data structure like that, or whatever. And then you say, new process comes in, they give me a chunk of size n. Okay? And first fit, you're just scanning the list to get the first one. In best fit, you are actually scanning the list to get the smallest one, that's greater than. And in the worst fit, you get the biggest one, and then you chop it. Okay? There's a question that was asked that said, why would you ever use worst fit? If you think about it, worst fit actually creates the biggest residual hole. By allocating the biggest chunk, you're going to be, what is left over is going to be big. In best fit, what happens is when you allocate the smallest hole that's good enough, the hole that's left over, because you will not get an exact fit. You will get something that's bigger than what you asked for. The hole that's left over is actually going to be small, and that may end up being wasted. That was the intuition beyond why you need worst fit. Although what you actually see is best fit actually still does better in terms of overall memory utilization, in terms of the amount of memory lost to fragmentation. Okay, first fit and worst fit do much worse than best fit in terms of memory loss to fragmentation. Okay. So that's external fragmentation. There's another one called internal fragmentation. So internal fragmentation is simply memory wasted inside a process rather than outside the process in holes. And why would you actually waste memory inside a process? So let's take this small example here. It says here's a process, it needs 8846 bytes. Okay, and you found a hole that's 8848 bytes. Okay, that's 2 bytes bigger than the size of the process. So you have one of 2 options. You give the process what it asked for, it's 8846 bytes. And now we have a 2 byte hole left over. Okay, it's completely useless. We never actually use that 2 bytes. Okay. And it's going to sit on your list of holes, it's going to make the list longer. And every time you scan it, you have to scan more entries, and that's just going to consume more space. The other thing you would do is, you say this is just bigger than what the process asked, so let me give it that entire region. Give it 2 bytes more than what it's needed, but you wasted those 2 bytes, and that's referred to as internal fragmentation. So internal fragmentation exists when the memory allocated to a process is greater than what it needs, so you're wasting memory inside a process. You did this simply because if you did not, you would have a very small hole that may be of no use at all. So you're better off just wasting memory inside the process but keeping the list of holes somewhat small. Yes.
There's a line of policies in Ready queue, and one of them is too large to be assigned a place member because it's not large, there's not a space large enough that's contiguous. Will it get like pushed back to non-priority and then modems the process is queued up because it can't fit in the hole?
Okay, so you ask if there's a queue of processes in the ready queue, okay, and you ask for memory. So first of all, you should realize if you're in the ready queue, you're already gone past the load stage of memory allocated to you. So this shouldn't have happened at all. Right? After you're in the ready queue, you're actually ready to run, you're already loaded in memory. But what you ask is a valid question. Let's say there's a queue of newly arrived processes, okay, other than processes in the ready queue. And you are saying what happens when there isn't enough memory. Okay, and you go to the end of the process. You could put it at the end of the queue. You could put it at the end, or you could throw an error saying there's not enough RAM. Most OSs will just throw an error. If you actually start forking a lot of processes, okay, next time you have your own machine, you can write an infinite fork process that does infinite fork, which sits in the while loop and starts working. After a while, you'll see an error saying there isn't enough memory to start the process because all these processes are getting allocated memory allocated to it, you run out of RAM. So you're not going to put these processes at the end of the queue. You simply say, I can't even run them and terminate them before they start. Okay, so you just give an error. Yes.
What difference does those 2 bytes make if you don't allocate it in? Because won't they rejoin, once that process ends, won't those 2 bytes rejoin the free space?
Yes, so the question is actually doing this is better is what we are arguing, not worse. Because having a 2-byte hole is worse because it just makes the list of holes longer. So when you're scanning them, you have more entries to scan. Searching in order, login, right? So everything takes more time. So it's better to actually give the process a little more than what it asks for. Not have a hole because eventually when the process ends, it will rejoin, as you rightly pointed out. So what we are trying to say here is internal fragmentation in these cases is better than external fragmentation. At least it will create more
than the maximum number of bytes you give it's 2 free bytes there, say it was like 30 or 40.
Yeah. So I think question is what you consider a hole that's small enough, configurable parameter, right? So you say in my operating system I will set the limit to 100 bytes. Whatever pick a value, it could be 1 kilobyte, it could be 10 kilobytes. You say whenever I have a hole that is smaller than that threshold, I just allocate the whole thing as base. That's strongly configured. There is no golden number. You have to pick it. What you consider is very small. So that's internal and external fragmentation. Okay. So what you do in your external fragmentation, you have to run a defragment operation, which is called compaction. Compaction actually involves moving processes around to create or recreate your contiguous set of unallocated memory, and that's basically what is shown here. So you have in this case OS and 2 processes C and D, okay? And then process E comes along, says it needs 600, there's no hole that's big enough. So you could, as I said, do one of 2 things, say, sorry, I cannot allocate this region because I do not have a hole that's big enough. Or you're going to say, I'm going to run compaction. I'm going to move these processes. Okay? So in this case, D is moved up, C is moved up, and then the free space, you have now a large chunk of free space at the end. That's the same as the unallocated space, and now E can fit in there. Okay, so this is simply a defragment operation. Okay, if you run a defragment, which we'll encounter in a few lectures, that's going to do the same thing in this case, moving files around, so free space on disk, which got defragmented similarly. Same thing happens on disk. When you allocate, deallocate files, you'll have holes on disk. That's what you will basically, when you run these defragment, this is what's going on. Files are being moved around, so free space is actually optimized. File layout is optimized. So here you are moving processes. Okay? And this is where dynamic reallocation helps. So we said one reason to move it is you want to grow the process. Another reason to move it is you want to defragment that memory. Okay, so when you move processes, you'll see that their base and limit values are going to change. The start locations and end locations change. The only thing you really have to do is next time the process runs, load the new values in the 2 registers and you're done. There's nothing else to change. It's completely process is unaware that it has been moved at all. So all this can be done without impacting process execution. Okay, it is of course slow because you're moving lots of memory around. So that part you cannot avoid, and you have to run this every once in a while when you have external fragmentation. Yes.
Is static relocation or dynamic relocation among the more common?
What's the question? Yeah, please.
Which is more common for memory management, dynamic relocation or static relocation?
Which is more common? Typically, it would be dynamic relocation. Static relocation is too simplistic. It cannot be used in a multi-program environment. If you have an embedded processor where you know only one program runs, you can use static relocation. A small set of programs that are not going to go. Any general purpose operating systems, you have to do dynamic. Actually, you don't even do dynamic. You do paging, which you will see in a moment. But dynamic is probably right thing. Okay, so every once in a while you have to run this defragment is going to do compaction, external fragmentation is going to go away at this point, and then you allocated in this example memory that we use for CS. How often do you run? Yeah, that's a good question. So just related to that question, here are two variants of compaction. Here you did full compaction. You took all the processes and you moved them up, you created one giant whole. Right? Here you did partial compaction. You said, I do not have enough space for E. What are some minimum number of processes I need to move around to create a big hole for E? And all you said is you can move D up and they create this big hole that's good enough for E. So that's partial. You didn't move everything. You moved some processes and you can remove some of your external fragmentation. Okay? Now, is that clear? So you can do partial or full. And now that goes back to the question of how frequently do you run it. A, it's expensive, you can't run it frequently. But anytime you hit external fragmentation, a process comes along, asks for memory, you don't have it, but there is enough speed memory that you can reclaim through compaction, you have to run it. You could also periodically run this in the background whenever you see that the number of holes is exceeding a value or whatever. You can do some policy like that and you run it. But it's not cheap. Okay, it's going to slow down the operation of your system because you're doing all this memory copying in the background. Okay, so you don't want to run it very frequently. Okay, there is no golden thing that says run it once a minute or once an hour.
Now it seems like there would be some times when like a process comes in, it can't fit in, there's enough space, but you wouldn't want to run compaction. Because, and I guess like compaction would take up a lot of processor time. And if in that time another process would finish naturally if we have enough space.
So you could, of course, do what you said, which is you queue it up for some period of time. Don't reject it immediately. That is what we call a long-term scheduler. Long time ago said there's some queue of processes that haven't just initiated and they are not actually running. So you just wait for some processes to depart, say that creates so. Otherwise you say, okay, I'm going to run compaction. So you say, I'm going to run compaction every 15 minutes. So either I make it wait for that long, and the process departs, I run it, otherwise you wait for the next quarter hour and I will run compaction and you can get the process. So you can use any policy, there is no particular technique that's good enough. Okay, so this is compaction and there's partial and there's complete, you can do all of these things. Okay, so there are many different compaction algorithms for doing partial compaction, saying how much to extract because it's expensive. Should you stop as soon as you create the first hole? Do you run a little longer, create a few more big holes, that way you don't have to run it again. So those are all variables. Yes.
I know we're talking mostly about single core machines, but on a multi-core machine, might compaction include moving process from one CPU to actually a different CPU, as opposed to just within the same one?
Okay. Question is, can you run it or move it from one CPU to another? So that is not related directly to memory management, related to scheduling. Because the RAM is still shared by all the cores. So if there's only one RAM, if you have 10 to 16 cores on a machine, there's still one RAM. All these processes are resident in RAM. It may be that this process is executing on core 1 and that process is executing on core 2, but they still share the same RAM. So when if you move them across CPUs, that's the CPU scheduler's job, saying next time I run it on a different core. It's not the job of the memory manager to decide which processes get mapped to which core. It's an independent issue. Okay? Okay, so we're done with compaction. So the last point I'm going to talk about is swapping, and then we will end it then today. So swapping is a technique that allows you to run more processes than you have RAM for. Okay? It's a very crude form of the next technique we are going to look at, which is staging. Okay? So what happens in swapping is there's an active process, and maybe it's waiting or is locked on a lock, is taking up some RAM. Okay, there are new processes that are coming in, but there isn't enough space, not due to fragmentation, but your memory is all in use. So what you could do is you temporarily swap out the process. You take whatever is in memory, you write it out to disk. Okay, all of its content get written out to disk. That frees up that memory. You run some other process there. Okay? And after a while, that process gets swapped out, you can bring the first process back in. Okay? So you could do this form of crude memory management where processes that are active in memory get temporarily written down to disk. While they're on disk, they cannot run. Okay, they have to at least be in the RAM to run. So you can say, I'm going to swap this process out, swap some other process in, some other process gets loaded in, you run it for some period of time, and that process goes out, some old processes come back in. So you can do this form of memory management. And what this achieves is a higher degree of multi-programming than if you didn't do it. Okay, otherwise, you're limited by size of RAM. Even with no fragmentation, you used up all of your RAM, you cannot run any new processes. At that point, you have to give an error saying, I don't have enough RAM to run anything more. Okay, there is simply not enough free space. Okay. What swapping allows you to do is run these additional processes. They won't be resident in RAM. It is going to slow down the execution of processes because you have to load and unload them from memory. But you can run more processes this way. So you can run, instead of n, you can run a lot more. Some of them will be on disk. Okay, the state is written out to disk and you load them back. So this is basically the technique of swapping. Again, dynamic relocation is going to help us there because next time you reload a process, there's no requirement that it go back to where it was previously. You can put it into any hole that is good enough for that process. So all you need to do is change your base and limit registers and you are good to go. Okay, so swapping works very well with dynamic relocation, not so with static relocation. With static relocation, anytime you move the process, you have to go and change all your assembly instruction addresses. And so that is going to take some time.
So reloading from disk experience the same difficulties with fragmentation and power quality.
So when you load and unload from disk, it's the same problem because loading the process from disk is like a newly arriving process. You have to find a hole that's big enough, and all of those problems still exist. You're simply compounding your problem because it looks like there are more arrivals and departures. Each swapping is like an arrival and a departure. So you may actually get more fragmentation and you may have to run more compaction as a result. Okay, so we are going to end it here. Next time we are going to look at more sophisticated C, and that will relax some more of these limitations.